Modern natural language processing strips away the literal strings of text we read and write. To a large language model, a sentence is not a sequence of letters, but a strict geometric structure in a continuous, high-dimensional vector space. To translate text into geometry, the model first subdivides a string of characters into tokens. It relies on a fixed vocabulary, mapping each substring to a discrete integer index. This chart shows the embedding step. A learned weight matrix, denoted as E, maps each discrete integer index to a specific row. By extracting and stacking these rows chronologically, an entire sentence becomes an ordered input matrix, X. Because this matrix alone treats words as an unordered bag of concepts, the model overlays additional positional embeddings onto the vectors, hard-coding the chronological sequence directly into the numerical values. By framing language as a geometric matrix, we can deploy the mechanics of linear algebra to calculate semantic meaning. This translation requires massive parameters. Llama 3 tracks 128,000 tokens with an 8,192 embedding dimension. Gemma 3 uses 262,000 tokens. When generating a response, these models operate in a continuous stream. To predict the next correct word, the model must calculate the geometric relationship of the new token against every single token that preceded it. Recalculating the entire sequence from scratch for every new token prediction is computationally expensive. The time complexity of this operation scales quadratically with the number of tokens in the sequence. To bypass this compute time, engineers use a technique called KV caching. Instead of recalculating past tokens, the model caches the previously computed matrix vectors directly into the GPU's RAM. This drops the compute time for new tokens down to a linear scale. But trading compute time for storage introduces a severe physical constraint. KV caching rapidly consumes available hardware RAM, establishing a hard memory barrier that strictly limits exactly how much context a language model can effectively retain. To see exactly what is being stored in that memory cache, we have to look at the core engine of the transformer architecture, the attention layer. The input matrix X multiplies 3 weight matrices, splitting into queries, keys, and values. Like a database, only keys and values are cached. Multiplying the query matrix by the transposed key matrix creates a massive grid of dot product similarity scores. These raw dot products are fed into a similarity metric function, specifically a scaled exponential kernel. Because the dot products of high-dimensional independent vectors grow excessively large, the formula divides the matrix by the square root of the embedding dimension. This stabilizes the variance to 1 before applying the exponential. Next, the model normalizes the output. It calculates the inverse of a diagonal matrix, Z, whose elements are the sum of the rows. Multiplying this by our scores yields a valid probability distribution across the tokens. The final attention equation is Y equals Z inverse times A times V. The normalized attention weights act as a strict filter against the semantic value matrix. Through pure matrix multiplication, the model dynamically measures the exact geometric relationship between tokens, using continuous vector similarity to establish context. Generative models, like the GPT family, construct sentences sequentially. This requires an architectural restriction known as masked causal attention. The model applies a contextual mask, M. This indicator matrix strictly prevents any given query from referencing the key value data of tokens that logically occur after it. By setting the masked elements to negative infinity, the math forces the probabilities of future tokens to precisely 0 once the exponential function is applied.
Without caching, generating these masked sequences forces the hardware to calculate full attention repeatedly, at a cost that grows with the square of the tokens. But the KV cache solution exacts a heavy toll. For every single token processed, the hardware must hold 2 distinct floating point values, multiplied by the number of layers, heads, tokens, and the embedding dimension. Storing these massive, high-dimensional key and value tensors across dozens of layers scales linearly. This data inevitably fills the GPU memory, imposing a hard ceiling on the model's context window. Standard multi-head attention dictates that for every parallel query head, there must be a unique key and value head calculated and stored. To mitigate the memory drain, models like Llama 3 and Gemma 3 employ a structural compromise called grouped query attention. Instead of maintaining independent caches, Grouped query attention forces multiple query heads to share a single, reduced set of key and value heads. This immediately cuts the size of the cache, but it sacrifices parameter capacity and model nuance just to squeeze more context into limited RAM. Grouped queries merely delay the inevitable memory wall. To build truly long context models, engineers needed an architecture that mathematically eliminated the full key and value matrices entirely. Multi-head latent attention, developed by DeepSeek, provides a mathematical bypass to the KV cache problem. Instead of caching massive key and value tensors, the model projects inputs into a shared, highly compressed latent space, this narrow matrix L. To retrieve data, L multiplies by small expansion matrices, mathematically factoring out to reconstruct the full-sized key and value matrices. The memory bottleneck is immediately resolved. The hardware no longer caches massive key and value tensors. It only stores the single, highly compressed L tensor. But there is an obvious flaw here. Reconstructing the complete key and value matrices from the latent vector at every single token step incurs a massive computational penalty. We have seemingly traded our memory problem back for a compute problem. The efficiency of latent attention relies on the associative properties of linear operations. Those expansion matrices do not actually need to be calculated at runtime. Instead, they can simply be absorbed. Because matrix multiplication is associative, adjacent weight matrices within the attention formula can be pre-computed and merged directly into the model's weights during training. First, the latent to query weights. Because the formulas sit adjacent, this matrix multiplies directly against the transposed latent to key weights, absorbing them into a single merged tensor. Next, the latent to value weights combine with the final output weights, creating a new consolidated latent output matrix. By merging the weights, the model directly calculates the final attention scores and outputs using only the compressed latent vector L. The key and value matrices have been mathematically eliminated from both the compute cycle and the hardware memory. There is one mathematical caveat: rotary position embeddings. Because these positional matrices must be applied after the key is constructed, they break the perfect associativity required for matrix absorption. Engineers account for this by appending a small, non-latent subset of data directly to the vectors, strictly for positional tracking. This slight break in the formula allows the model to retain positional awareness while keeping the vast majority of the sequence compressed. Overcoming hardware limits is a problem of applied mathematics. By re-engineering the attention mechanism's geometry, we dissolve the memory bottlenecks previously hard-coded into the architecture.